东西没有问题。Hey, Julian, do you want me to share screen?
Yes, you can.
Um, does it look right?
Looks good.
Okay.
我现在在最后 last minute， 我在 post 你的 talk info 在那个 Facebook 上，你等我一下，我现在 post。我是已经有advertise， 但是就是 in case 有时候可能大家最后一秒才会去看 Facebook。What has changed since last time？ 自从上次之后有什么改变了 ？Parameter， 我上次
What do you mean by change?
说不定有 new progress, whatever exciting things or whatever.
Not much. I mean, the weather is now better, so.
最近有 travel 吗？有需要 travel？
I hope. 但实际上没有。Well, you? Have you been traveling?
Not really, not much.
Not much.
I think last time I did, but it wasn't not very much. Permit 的 silver lake 还在吗 ？Permit 的 silver lake，silver lake，那边不是有个湖吗？
Oh,
公
yeah,
湖
still there. I mean, there's some construction works going on at the park, but the lake still exists. Yeah. I mean, it's not a lake; it's a, I don't know, pond or something.
There's still some wildlife.
Yeah, they're like.
So there's also a small zoo
Oh
nearby.
yeah. That's still there.
Yeah, I used to jog there, and also the water reservoir nearby. Still some nice wildlife.
Yeah, those are all still there. I mean,
Okay, the wildlife still
Yeah.
still
yeah, they survived the pandemic fine, unlike human beings.
okay. During the springtime, you will see a lot of little ducks and no, just the ducks, the adult ducks, and carry around the little children. You'll see a lot of little ducks. I think it's about the time, you know. I think we can start. Let me just press loading. Welcome everyone to Harvard CMSA Quantum Math and Physics Seminar Series. 欢迎各位参加 seminar. And it's our great honor to invite Professor Chong Wang from Perimeter Institute. And Chong is a well-known member for many people here at Harvard and MIT. He studied at MIT for his PhD and went to Harvard for his junior fellow. And currently he is a faculty at the Perimeter Institute. He's known for his many magicians type of style of works in quantum matter. And it's also a style I really enjoy looking his work. Today he will be speaking about his recent work on non-zero momentum require long-range entanglement. Let me remind the audience one more time, please. Please really just feel free to interact with Chong and ask questions during the talk. And it's really your questions make the seminar interesting. Help the seminar to be even more interesting. So just join us and welcome Chong. All yours, please. Thank you.
All right. Thanks, Juven, for this opportunity to speak and for the nice words introducing me. So today I'm going to tell you a recent story that's actually a pretty simple story. So it's done with my student Lei Joya at Perimeter, and here's the reference if you want to see more detail. And by the way, Juven, do you see my mouse pointer correctly?
Yes.
Okay, good. Yeah. So in case you have to leave right now, this is my message for today. So let's think about a lattice spin or lattice boson systems in any dimension, really. And think about a quantum state, a general many-body quantum state that's an eigenstate of the lattice translation operator. The only requirement I put on it is that it has a non-trivial eigenvalue under the translation operator. So essentially under translation, it goes to itself with a non-trivial phase factor that's not equal to 1. Namely, it has a non-zero lattice momentum. And the claim is that this state, this simple fact is enough to guarantee that this state is long-range entangled. And the rest of the talk will basically be two things, justifying this statement, hopefully with a proof. And then I'll talk about two applications of this theorem, if you like. One is on various types of Lieb-Schultz-Mattis theorems, and another is about what's called the weak symmetry breaking, and particularly weak translation symmetry breaking in topological orders in dimension 2 and above. But before that, let me first go through the introduction of the notion of long-range entanglement. I'm sure a lot of you here know this very well, but let me just make sure that we're all on the same page.
Tom, can I see one more time the claim in the beginning?
Yes.
D is the space dimension, right?
Sorry?
D is the space dimension.
Yes. Yeah, I'll repeat this statement quite a few times as we go. But yeah, basically the statement is a quantum state with a non-zero lattice momentum has to be long-range entangled. Yeah.
Can I ask a really basic question about the result?
Yes.
I mean, maybe you'll answer this, but it seems like long-range entangled needs to be defined in the thermodynamic limit, but the momentum eigenvalue seems to be required to be on a finite system to be defined.
Yes.
So how do you reconcile these statements?
Yeah, I will answer that. So the statement is that if you define long-range entanglement in terms of a finite depth local unitary, then my requirement is that the system size is much larger than the depth of the circuit. So in fact, the statement can be even stronger. Basically, the statement is that if you want to prepare such a state, the depth of the circuit has to be of order n.
Okay, thanks.
Yeah.
And this momentum is any direction, just any of one of the direction.
Yeah.
Okay. Does not need to be all direction in the space. Just one.
Yeah, any direction. Just one of the direction has this. That's enough. Okay. So basic notions. Let me first introduce you what is short-range entanglement. So two states, just let's say psi 0 and psi 1, are said to be in the same phase or family of states if they are related through a local unitary evolution, or basically an adiabatic evolution in finite time. Okay, so these are the symbols. And this is basically motivated by the notion that two states adiabatically connected to each other are considered to be really the same phase. This notion goes back to as early as Landau, for example. And the short-range entangled states are defined as those that are adiabatically connected to product states. Right. So just think about, for example, a lattice spin system, and this product state can be things like up, all spin up, or up, down, whatever you like. Okay. And an important conclusion you can draw from this very definition is that such short-range entangled states can be realized as the unique gapped ground state of some local Hamiltonian. Essentially, the product state can obviously be realized as the unique gap ground state of some local Hamiltonian, just one qubit Hamiltonian, and from that you can just turn on the adiabatic evolution and get the parent Hamiltonian for this short-range entangled state, and it's going to be gapped and unique. And long-range entangled states are defined as whatever that's not short-range entangled, right? So LRE, by definition, are not adiabatically connected to any product state. And which means that if such a long-range entangled state is realized as the ground state of some local Hamiltonian, then it cannot be the unique gap ground state. So the options are either having gapless excitation spectrum, things like metals, quantum critical states, or you have gapped ground state, but with a degenerate ground state. These include things like topological orders or cast states from the spontaneous breaking of discrete symmetries. And that's partly why we we all love the long-range entangled states so much because many of the cool stuff in modern quantum many-body physics belong to this category. And for my talk today, turns out it's a little bit more convenient to use an equivalent formulation for the adiabatic evolution instead of thinking about adiabatic evolution in continuous time. It turns out to be a bit more conceptually cleaner and easier to think about a pretty much equivalent formulation in terms of the finite depth quantum circuit. This is a common practice in the literature. So essentially, we can approximate a finite time unitary evolution with a finite depth quantum circuit. So this is the figure of the circuit, and so this box is some in this figure is some 2-qubit gate. It can be any finite. It can be a gate that involves a finite patch of my region, and each layer consists of commuting such operators. And the point is that the whole unitary operator is the composition of a finitely many such layers. Okay. And in this formulation, a short-range entangled state is defined as a state that I can prepare out of a product state, let's say, for example, all zero, with a finite depth local circuit, with a finite depth circuit. And the depth of the circuit, you can roughly think of it as the correlation length of my short-range entangled state. Okay. And so now
Excuse me?
Yes.
I'm wondering if I could think of this short-range entangled state just as some kind of MPS with order 1 bound dimension.
In 1D, you could.
In 1D, let's see.
You almost could. There are some things you have to be a little bit careful. In 1D, you have to make sure it's not a cast state. Cast state doesn't count as short-range entangled in this definition, but
okay,
for most part, it can.
Okay, thanks.
Yeah. So you mentioned that you want to ignore the exponential tails, but I think there are cases where exponential tails are kind of important, right? There are like SPT states what can be disentangled by a circuit with exponential tails, but not by a strictly finite depth circuit. But you're not going to worry about that?
I'm not going to worry about that. Yeah. But, yeah. So I'm going to assume that it doesn't qualitatively change my argument, but I don't really have a good proof of that.
Okay.
But also for those examples that it's usually easier to have circuits that disentangle the state rather than disentangle the Hamiltonian. But those are some higher order things. Bottom line is, I assume that it doesn't matter.
Actually, another naive question.
Yes.
Yeah, like the theorem here, do you consider gap system or gap the system or just?
Yeah, for this statement, I don't even need a Hamiltonian. This is a statement on the state. Right. So, but of course, if the state is realized as the ground state of some Hamiltonian, then the statement is that that Hamiltonian cannot have a unique gap state. Okay. Right. So now I can phrase my the claim a little bit more precisely. The statement is that if I have a quantum state, let's again consider bosonic or spin system, with a non-trivial lattice momentum, then the state is long-range entangled in the sense that it cannot be connected to a product state through a finite depth circuit. In fact, turns out that to prepare such a state, what you need is a circuit depth m of order of the system size. So even if you take, let's say, m to be not finite, but log L or polynomial of log L, it won't change the statement. Right. So and the intuition behind this statement is actually extremely simple. Let's say you think about a product state of this form, right? So A1 tensor A2 and so on, and you put it on a ring, right? The ring is the topology you need to even define translation symmetry properly with periodic boundary condition. So when you act with a translation operator, this state goes to this, right? A1 goes to A2 and AL goes to A1. And you stare at it, you realize that the only translation eigenstate that you can have out of such product state has this form, which can only have trivial momentum. Right? There's no product state that you can have to get a non-trivial momentum. So if you so the statement is that a product state cannot have non-trivial momentum. And next, what I'm going to show is that even if you act on this product state with a finite depth circuit or a circuit with depth much smaller than L, the system size, it cannot change this fact. Right? Basically, you cannot boost the momentum of a product state with a short quantum circuit. And so now I'm going to show you the argument. But in case
can I ask a really silly question?
Yeah.
I mean, what if I just take one downspin moving in a background of upspins in a finite momentum state?
Exactly.
You're saying that state is long-range entangled?
Yes. It's somewhat. It almost sounds like a trivial statement, but yes. There are two ways you can see it.
Silly definition of long-range entanglement.
There are two ways to see it. One is even though that state looks very trivial, if you calculate let's say some 2-point connected correlation function for some operator, you'll easily find things like it goes like 1 over L or 1 over L squared, where L is the system size. So that's not quite an exponential decay. That's a parallel decay. Another way to see it is that if you ever realize such a state as the ground state of a local Hamiltonian, then that Hamiltonian that ground state must be gapless, because you can essentially, because if you change that momentum from K to K plus 2 pi over L, the energy cost will necessarily vanish as 1 over L. There are actual papers discussing this point. So as trivial as this state looks, it actually counts as a long-range entangled state in this definition.
I mean, what if you have a Hamiltonian where you just break, 2 sublattice symmetry and you get a charge density wave of wave vector pi? That doesn't have any gap. That does have a gap. Sorry.
Yeah, the thing is, you're gonna get a twofold degenerate, almost degenerate.
I see. I see. Okay.
The plus and minus superposition. The minus superposition has the pi momentum.
Right.
Right. So and without, as long as you keep the translation, these two are degenerate. So there's no adiabatic path from that to a trivial symmetric state.
Okay, thanks.
Yeah. So the statement is that if you realize there's the ground state of some Hamiltonian, it has to there must be some gaplessness or degeneracy, even in the somewhat trivial sense.
Chong, could I sorry, this is Andrzej Niewiadomski. Could I also ask you somewhat maybe trivial question?
Sure.
So let's take I want to say system of fermions, but it's not important at this moment whether the bosons are fermions. If I have a periodic lattice potential, right, I could always formulate a Bloch theorem.
Yeah.
And so in some sense, what you're saying is that a Bloch state, which by definition is an eigenstate of a definite k momentum, is not connected in an infinite periodic system to a product state by any finite depth circuit.
Yes.
Right?
A single particle Bloch state.
Exactly. Right. Single particle Bloch state. But the single particle Bloch state could be, I don't know, gallium arsenide, could be an insulator. It doesn't have to be gapped. There is no obvious degeneracy. And yet what you're saying would appear to be true.
Yes.
So didn't you just say that you need either degeneracy or some gaplessness?
No. Yeah. So the statement is if you have a single particle state, so for example, you say the ground state has some momentum. Yep. Let's say that particle has some momentum k. The statement is if the Hamiltonian is local, then you can show that if you change that momentum from k to k plus 2 pi over L, the energy cost will vanish as 1 over L. So it's actually gapless.
Oh, I see. So you're referring just the periodicity of the Brion zone.
Yeah.
Okay, and just to follow up on this, so in some sense, what you're saying is that what nature naturally does for us in a thermodynamic limit is applying essentially a infinite depth quantum circuit to get us the Bloch theorem. Again, I'm not trying to sound controversial here, but it sounds like the statement is either almost trivial or it's very deep, and I'm not sure how to think of it.
Sorry, Chong, I thought your theorem is about the many-body ground state, not the single.
States. So when you talk, exactly. So when you talk about a Bloch state, the closest thing resemblance is what Subir described. So it's let's say for example with all spin down, but with a spin up, but put that spin up into some Bloch state. That's long range entangled.
Okay, but then right, but okay, I could think of slate determinant as also a single particle state, right? So you're saying that any
but Slater determinant is different. The point is if it's an insulator, the Slater determinant will always have trivial momentum up to some pi. That's because of the fermionness. But if you neglect that, let's say your system size is odd, so pi momentum doesn't exist. Then you'll find that a filled band will always have trivial momentum.
Oh, if you sum over all single particle states.
Exactly. Okay, the only way you can get non-trivial momentum is to have partially filled band.
I see.
And that's gapless. That's a metal. It's the most long-range entangled thing out there. Almost.
Okay, and sorry, I don't want to stop you anymore, but one quick thing. What about Galilean invariance? If I consider my insulator traveling in a not lapped frame with momentum p,
it's not obvious to me whether this generalizes to continuous momentum or how. For lattice, at least for lattice, I know there's a clear notion of trivial states. That's the product state. Now, if you have continuous translation symmetry, you have to be careful what you mean by trivial state.
So can I comment on that? If your argument that you were making about you boost the system will only work if you're a non-zero charge density. And non-zero charge density, there's another LSM theorem that says you have to be gapless.
Sorry. Dominic, can you repeat that statement?
So if you want to say that you have some state and then you oh no, sorry. Yeah, sorry. Ignore my statement. That was stupid.
All right. So I'll continue. Feel free to raise more questions if it comes up. Okay. All right. So well, the idea is that let's say suppose we have some. Let me first give you the rough idea of the argument, and go into the more details of the proof if I actually have that much time. So suppose I have a short-range entangled state. By definition, meaning that it can be it's created out of the trivial product state, let's say all zero. By the way, I'll keep saying qubit, but think of it as any finite dimension or local Hilbert space. And let me also just argue in one dimension. It turns out that's pretty much enough. It's fairly easy to generalize it to higher dimension once we have the 1D result. So think about a short-range entangled state, which by definition is prepared out of the product state with a finite depth circuit. Let's say the depth is m. And what I'm going to show is that if the system size L is much larger than m, and if the state is an eigenstate of the translation operator, then the momentum must be 0. The eigenvalue must be 1. Okay. Of course, this circuit U, I am not assuming this U to commute with the translations operator. Otherwise, it will be a totally trivial statement. So U in general does not commute with translation. Okay. So the idea of the proof is basically to try our best to convert this short-range entangled state, this psi, into some kind of product state for which we know the momentum must be trivial. But the trick is, whether we can do that without, for example, changing the original momentum p. The trick to do that is basically to use the circuit that trivializes this state and use this very circuit, part of this circuit, to disentangle the state on some links, right? So if you apply this full circuit U, then by definition, I completely trivialized my state psi into just 0, 0, 0, 0. But one thing you can do is to just apply the gates in this blue triangle, in this blue light cone. So this guy. Everything out of this light cone region won't be touched. So it still locally looks like the original psi. But this, at least in this example, these two qubits are turned into trivial product state, like the 0. Right? So the entanglement across this link is cut, is removed by this light cone circuit. Right? And the fact that this circuit U has finite depth ensures that this light cone only has finite support. Right? So it only affects a finite number of qubits in my original system.
Sorry, can I ask a question? So in this picture, you're assuming like a nearest neighbor form for U?
Yeah, for convenience, in general, U can be any finite thing, but of course you can always make up a finite, any finite qubit gate.
Yeah,
with 2 qubit
that's
gates.
fair.
Yeah.
Like for example, I know that you can say like, okay, for each term in U, you have finite support. But the thing is, can you have infinite terms in U, for example?
Sorry, what do you mean by infinite?
Like, let's say I just take a formal sum of like a bunch of finitely supported operators, right? Each term is finitely supported, but like the whole thing doesn't have to be, right? Because we don't know how many terms there are essentially. Is that, or does that violate like?
Sorry, I may have misunderstood you. What do you mean by formal sum? What are you adding?
Like just a sum of operators, right? But you.
Yeah, here you have to be a little bit careful about. I'm not summing any operator. That's a thing that's yeah. Here by this picture, it's a product of these operators.
Yeah. What? Sorry, never mind. Then yeah, it's just that under this understanding, you're working with a operator with fixed support.
Yeah.
Okay. Okay. That's all. Thank you.
Yeah. So if I cut it just at one link, it doesn't really buy me much. But the thing is, I can use this same trick to cut at essentially any place I want, right? So let's say if I call this u tilde 0, I define it as the cut using this light cone circuit at the first link. Let's say the link between the Lth and the first qubit, for example. And then I can translate this operator, this light cone cutting operator by conjugating it using the translation operator. And the fact that my original state psi is an eigenstate of the translation operator guarantees that the translated version of the of u0, let's call it ui. Sorry, I think this should there should be a power I here, so I translate by I times. It guarantees that if I act on my original state with this ui, then I remove the entanglement between the ith and I plus 1's qubit. So notice that this ui is not necessarily the light cone circuit, the light cone gates at the sorry, the light cone gates for the u operator at the ith link. Rather, is the translated version of the light cone at the 0th qubit. Okay? Because the u quantum circuit is not assumed to be translational invariant. So these two things are in general different. Okay? However, the fact that my original state is a translation eigenstate guarantees that even though this u tilde I is not quite the light cone operator at the ith link, it nevertheless removes the entanglement at the ith link. Okay? So it works just fine. Anyway, that's actually some detail, but the point is that equipped with this, I can now try to cut my system at several different locations simultaneously, and essentially convert my system into a product state, but now with a larger unit cell. Right? Previously I showed you that if I have literally a product state with a unit cell of 1 qubit, then the ground state, the momentum has to be trivial. But now, let's say, for example, if my system size is n times L, it's a little n times this capital L, then I can cut the system using this trick at every, sorry, I think this is a typo here, at every L link. Right, so at link 0, I can make the cut. At link L, I can make the cut to L, and so on. Right. So this is an example with little n equal to 4. So I'm cutting my system into 4 length L subsystems. Right, and these 4 subsystems are disentangled from each other. Right. So if I view each length L patch as just a larger unit cell, this is just a product state of 4 patches. Okay. And the important thing is, even though when you apply the cut at each point, you break the translation symmetry, if you do this, you are keeping a subgroup of the translation symmetry, which is translation by L unit cells. Right. For example, in this picture, it's clearer when you stare at the picture. Even though this picture breaks the fundamental translation symmetry, but if you translate by L unit cells, which is the length of this patch, the system goes back to itself. The circuit goes back to itself. Okay? So I can talk about so this is now a product state of length L unit cells. In this case, 4 of those, which preserves the L-fold translation, which is an eigenstate of the L-fold translation. So now you just apply the statement we just made there. A product state has trivial momentum. Then this coarse-grained product state, if you like, must have trivial momentum under the L-fold translation. Okay. So meaning sorry, meaning this psi tilde to the tensor to power n has one eigenvalue under translation. However, since this this circuit preserves the translation, the eigenvalue should be the same as my original psi, right? So but for my original psi, the eigenvalue under L-fold translation is just it's just L times my original momentum, right? So this is basically saying that L times my original momentum P must be 0 mod 2 pi, right? As long as my system size is n times L. Okay? And the only thing I need for this argument to hold is that L is much larger than the circuit depth M, right? Because I want the light cone circuits here to be independent from my light cone circuits here, right? Because M will be the support, the size of the support for each of these cutting unitaries. Right? So as long as L is much larger than M, then this statement holds. Okay? So this is really there's a very similar argument in this classic paper by Song et al. About classifying crystalline SPT phases in higher dimensions using the trick of dimension reduction. Again, the fact that with a short-range entangled state you can come up with such cutting operators is important.
Excuse me.
Yes.
What the notation of the P, the psi state of a P of NL compared to with the psi tilde of L? Just maybe the notation. Can you? Yeah.
So good. Okay. So this psi is my original state. This W is the composition of all the cutting operators at 0, L, 2L, and so on. And the statement is that after applying this cutting operator, this state becomes the tensor product of identical states on this, in this case, the 4 patches or the M patches. And this psi tilde L is the state on each patch. Right? The statement is the psi tilde L could be horribly complicated, doesn't matter. But as long as the whole system is the identical tensor product of this psi tilde L, then it has to be trivial under translation by L side.
And the P of NL means the momentum.
So the momentum for the original state, for the original size NL state.
Right. No problem. I get it. Yes, thanks.
Wait. So is there a relationship between P and N, or are they independent of each other?
Right now they are independent of each other. Right now, actually, this is more like notation to prepare for later part, because right now I'm not really changing N and L, so P is just the momentum of some state that lives on this NL side system.
Okay.
Chong, I lost track of the logic a little bit. So you're trying to prove the statement. So what statement are you trying to prove? Are you doing reductio ad absurdum? Like, I'm confused.
The statement I'm trying to prove is that P eventually is 0.
Right, but didn't you assume to start with that the P is 0?
No. So the starting point is that this psi is connected to the product state through a depth M circuit with the depth much smaller than my size L.
Gotcha. And you're going to prove that as a result, the expectation value of momentum on such a state is 0.
Yes. Assuming that psi is an eigenstate of the translation, I'm going to assume that the eigenvalue must be 0.
Okay.
Yeah.
Thanks.
Sorry, I'm still a little bit confused. So where did n come from? Like here, you're assuming your size of the system is times L.
Yeah. I'm just assuming that. Yeah.
Okay, so I guess this is an intermediate step, but would this argument hold if your system is prime, like has prime size?
It will come up in 2 slides, but no.
Okay.
You need to do extra work.
Okay. Thanks.
Yeah. Actually, I'm getting there. So now I'm just rewriting my equation here. L times P equal to 0 on system size NL if L is much larger than my circuit depth. So now if I think about a special type of system size, let's call it L prime, that can factorize into P and Q, with P and Q being co-prime, but both much larger than my circuit depth C. Then I can replace this L by N here essentially, right? So essentially essentially I'll get an equation that looks like P times little p times this momentum should be 0 mod 2 pi, and little q times this momentum should also be 0 mod 2 pi. But if P and Q are co-prime, the only solution for this equation is that the momentum P itself must be 0 mod 2 pi. Okay. So I've proved my claim, at least for this special type of system size, that the momentum you get out of this finite depth circuit, or a circuit with a depth much smaller than the system size, must be 0 if it factorizes like this. Okay. But if you think about it, most large integers are like that. So if you are not too rigorous about things, this is pretty much a proof, I would say. Right? But if you are still very careful, you say, okay, if my system size is some, let's say, large prime number, or the power, a single prime number raised to some power, and so on, there are many examples you can come up with that doesn't factorize this way, right? Then this argument doesn't quite work, at least not yet.
Excuse me. What's the relation between the earlier system sizes n times L versus the one that you take right now, the L tilde? Just make sure.
Yeah. So it's basically a special type of system size. So essentially, the idea is that if you stare at this equation, there's no reason why it has to be L here. You can take N here. Essentially, if you have a system size P times Q, you can decide to cut it into Q copies of length P subsystems, or you can decide to cut it into P copies of length Q subsystems. And for both ways of cutting, you have a statement of this sort. If P and Q are both large enough, and if P and Q are co-prime, the only simultaneous solution for these two equations is the trivial solution.
I just want to make sure, how do you plug in the first equation how do you plug in the L tilde into the first top equation?
Oh, yeah. So essentially, so this little n times capital L will be my L tilde.
Yes.
So the way to plug it in is there are two equations you can now plug it in. You can have P, little p, times the capital P equal to 0.
And you can
then the little q
times
capital P equal to 0. So these are these two equations. I'm just divided by.
Again, yes. And little n was chosen to be P or Q.
Yes.
Yeah, thanks.
Yeah. Okay. So that's I call it step one. For this type of system size that concludes the proof. For more general system size, you have to do actual work. So the idea is that, for a general L, if you really think about the fact that you have your momentum created out of the trivial product state with a short circuit, with a finite-depth circuit, if you really think about it, you realize that the momentum has to come from some local region. And that's already a hint that the momentum must be trivial, because momentum is not supposed to be local. But here's this precise statement. So let me try to make that statement precise. So again, I have my short-range entangled state. I'm going to argue or prove that P, the translation eigenvalue, must be 0. Again, let me call it V. It's the inverse of the U I used before. So it's created out of the trivial vacuum, trivial product state with a operator V. Then the statement, the very fact that this has translation eigenvalue P means that this statement is correct. So this V, if I composite that with V dagger, but now translated by one unit cell, then it gives me back, when acting on the trivial product state, it gives me back the trivial product state, but with the momentum phase factor. Right? This is just because VL times Z times 0 is just my psi. So acting on this psi with this T dagger just gives me this factor e to the minus P. And then further acting on VL dagger just annihilates this V and get the product state. And then acting further with the translation on the product state gives me just 1. So it's a simple algebra. So in terms of circuit, it looks like this. So I start from 0, the product state, act with the VL, I get my psi, and then act with the VL dagger, but now conjugated by translation, I get back my trivial product state, but now with an extra phase factor. Right? So this is the circuit way of representing this fact. This will turn out to be useful, because this allows us to sort of localize the momentum in the following sense. So again, very similar to the trick I used before for this U operator. I can think about cutting a light cone out of this combined circuit, right? In particular, I can think of this combined object, which, let me remind you, when acting on the trivial product state, gives me just a phase factor, as the product of this V2, V2 meaning all the products of all the gates outside of this light cone. So everything in this enclosed by this yellow line, and then combined with the blue part, this V1, which includes all the gates within this light cone, and and this ordering of the product is important. This light cone structure, or basically the causality structure, ensures that when you split the operator into the operator within light cone and without, this is the correct way of ordering. Okay. And the fact that when this combined circuit act on the 0 state gives you back 0 with a phase factor means that if you think about, if you act on the trivial 0 state with just the out of light cone circuit, this V2, this guy's out of the light cone, then out of this blue region, in this yellow region, it should just give you back the trivial product state, right? Because the combined thing gives you the product state, and the blue circuits only act non-trivially within the light cone region. right? So which means out of the light cone region, the yellow circuit must have already given you back the trivial product state. Okay. And then tensor product with some presumably non-trivial state within the light cone region, in the blue region. Okay. And then you act on this, you further act on this state by the V1, the blue circuit. Well, we know that even it's going to give you the totally trivial product state, the zero state with a phase factor. The only way that can happen is that when V act on this alpha state, the state in this blue region, it converts whatever alpha it is there into the trivial product state, but with this phase factor, e to the minus p. Right. So the bottom line is that you can attribute the momentum entirely to this light cone circuit, the blue circuit, that, when acting on this appropriate state alpha, gives you a trivial state, but with the correct phase factor e to the minus I p. Okay. So why is that important? Well, this is important because as long as the momentum comes from a local contribution, we can take multiple copies and glue things together. So this is the trick we're going to do. The trick is, yeah, question?
Sorry, can you remind us, if you change the momentum from, maybe increase the momentum, how does the light cone shape for the blue and the yellow change?
The light cone shape doesn't depend on momentum. Here I'm not assuming anything about the momentum. The light cone is just, this is really depend on the depth of the circuit, for example. But that's it. If I fix the depth of the circuit, then the light cone just looks like this.
Yeah, I actually wanted to ask something about that. So depending on the depth of the circuit, you can have like light cones that overlap, right? So the support of these VL1, VL2, they can overlap, right?
You mean this region?
No, like just the fact that you maybe I'm misunderstanding. Like, for example, you take one light cone and then define the other light cone, quote unquote, as the complements. Is that?
Yeah. So V2 is not, it's not really a light cone. It's out of the light cone.
Okay. I see. Okay.
Within the light cone.
Yeah. Thank you.
Actually, sorry, could you repeat again why you know that the phase associated with VL2 is trivial?
No, I don't know that. The thing is, you can always define it that way. Right?
Okay, very good. Yeah.
Okay, so
sorry, just make sure. Maybe I missed something. Why is the light cone shape? Is the chosen one nothing to do with the given state or the momentum you want to start with? Just can you remind me again of that?
Oh, because I don't know my momentum yet. The only thing I know is that this is a finite depth circuit, and I'm just cutting a circuit into a light cone and its complement. For any circuit, I can do that. Well, at least if the circuit depth is much smaller than the system size, there will be no issue. Yeah.
The reason you need to choose a light cone shape, not other shape, is because.
It's because the causality structure. It's separated so that this yellow thing has nothing to do with the blue region. It doesn't really do anything. Sorry, I said the opposite. I should have said the blue circuit doesn't have anything to do with the yellow region, the out of the light cone region. The yellow thing does do something on this blue qubits. It converts the zero into this alpha. But the blue thing only acts non-trivially on that alpha. It doesn't act, for example, it doesn't do anything on this out of light cone qubits. Just by staring at this figure, you realize that that's true.
Thanks. Thank you.
And just a quick question: besides the initial set of states that you're choosing for the blue circuit, that also doesn't matter?
Sorry, can you repeat the question?
Like in this picture, you're choosing two sites in the blue circuit that you're propagating forward. That distance also doesn't matter.
that doesn't actually matter. This is just for convenience of drawing.
Okay.
All right. So why does that help? Well, now you can think about one operation. So previously, we were taking some system size and cutting the system into smaller pieces, essentially, right? Now let's do the reverse. Let's take several identical copies of the state, let's say n copies, and glue them together, right? The reverse kind of what we did. Let's say you take a system size L, the state prepared from the product state, and now you take n copies. Now you can glue the circuit together and define a new state on a system size NL, on an NL site system. The way you glue the state is basically just to glue the gates that gives you the original state. Essentially, let's say if originally you have at each layer, let's say if originally you have a gate connecting the Lth qubit with the first qubit, since you have periodic boundary condition, for example. Now instead of connecting Lth to the first, you connect the Lth to the L plus one circuit. L plus one qubit. Right. And if originally in a layer that you don't have a gate connecting the qubit L and qubit 1, then you just leave it there. It doesn't change. Right. So you're just gluing the state in the most intuitive way. Okay. And the claim that I'm going to make is that if you glue the state this way, then on the new system, on the new size NL system, you get a new state, which is also an eigenstate of the translation operator with momentum P now on system size NL. That's n times the original momentum P on size L. Essentially, the momentum just adds up. That's the claim. And you can see that because the momentum comes locally. So here's the idea. So to measure the momentum or to see the momentum again, you can consider this combined circuit. So this VNL is the glued circuit for this NL site system, and again we'll combine that with this dagger, but now conjugated by a translation operator. So again, if when acting on the trivial zero state, this system again gives you a trivial zero state with a phase factor, then you know that this VNL circuit creates a momentum eigenstate with the momentum given by this phase factor. So now let's think about this combined circuit, and again we cut it into light cones, except now I'm cutting the same light cone on each copies, on each of the n copies, right? So for example, in this figure, I'm having 2 copies of my original state glued together. So now when I define my the V2 and V1, so V1 has a light cone region for each original copy. So it's now 2 copies of the light cone region. The important thing is because of the finiteness of the circuit depth, or the fact that the circuit depth is much smaller than L, these 2 regions are far separated. They don't talk to each other. You don't need to worry about overlap and so on. Okay. And the orange one, the V2, is just whatever complement it is. And again, the causality structure guarantees that this is the right way to order the operator. So same logic as before. When you first act on the zero state with this V2, well, it's just this. It's just the trivial state in the yellow or orange region, and in the two blue region here, you get some non-trivial alpha state. Right? And now you further act on that with the V1, the light cone circuit. Well, that's just your original light cone circuit acting on each individual alpha. And from the previous argument, we know that acting on this VL on this alpha just give you back the trivial product state, but with the phase factor e to the minus I p. So now you have n identical copies. It just gives you this phase factor e to the minus I n times p, and then times the trivial product state. So so this shows that the glued state or the glued circuit still gives you a translation eigenstate with the momentum p nl, just n times the original pl. Okay. And that works as long as L is much larger than your circuit depth. It doesn't matter what n is. I mean, it has to be a positive integer, but that's it. Right? In particular, you can choose n, this little n, to be large and co-prime with L. You can always do that. And then we're back to step one, right? Because now we have a system size NL that factorize into two products of two large and co-prime numbers. And from the previous cutting argument, we know that this P and L must be 0, which means that this n times PL must be 0. But if n and L are co-prime, the only solution to this equation is that P is 0. I mean, one way to see that is to realize that PL is quantized. It has to be 2 pi integer over L. And if n and L are co-prime, the only solution to that equation is just P equal to 0. Okay. So that's basically it. That's an argument that the momentum has to be trivial on any system size. So just to recap, so I've gone through quite a bit of details, but the basic idea is that if the system size is P times Q, where both P and Q are much larger than the circuit depth, which I take to be fixed, then we can adiabatically cut this state into some coarse-grained version of product state. And from that, we can argue that the momentum has to be trivial. So that's for this special set of system size. And for more general system size L, we can essentially glue n identical copies of the state into a state on a larger system size, on the system size NL, but where the momentum is just the summation of the original momentum. So the momentum on this NL is just n times the original momentum. And you can choose little n to be large and co-prime with L to argue that the original momentum must also be 0. Okay. So essentially cutting and gluing, that's it. So this completes the proof in 1D. Right. And the nice thing here is that once you know how it works in 1D, it's almost a one-liner just to go to higher dimension, right? Because if you have a short-range entangled state in higher dimension, it's automatically a short-range entangled state when you view it as a 1D state, right? Because if it's prepared out of the product state using a finite-depth circuit in higher dimension, that circuit is also finite depth when you view it as a 1D circuit. It just has a larger unit cell. The unit cell has, for example, Ly qubits. But other than that, it's just an ordinary looking 1D state. So the original statement about 1D will just apply straightforwardly. So basically, the statement is for a higher dimensional state, as long as the momentum is non-trivial in some direction, then you can always roll it up. View the system as quasi 1D in that direction. And so if it's short-range entangled, it must have zero momentum. Okay. And that's basically it for the proof. Next, I'm going to talk about some applications of this statement, assuming it's true. But before that, is there any further question on the argument part?
Would you like to make any comments about how in IDMRG, the infinite DMRG, people study the cases where the state may have a finite momentum in the x direction, right? So they cook up a state that essentially, assuming the length is infinite in the x direction, but in a circumference, it could indeed be a product state or something short-range entangled. Does that violate the theorem? Does that tell you that that state just has been somehow constructed with infinite depth quantum circuit? How should I think about it?
Can you say again what state are you talking about?
Well, so I was referring to a general setup. I could give you a couple of concrete examples. For instance, I don't know, in a case when people like Mike Zalatal try to study so-called fragile topological states in the context of Moray, they would put it on a system where they would deliberately say, well, the state has a finite momentum k in the x direction, but it's sort of product state or otherwise short-range entangled in the y direction, right? And I guess the statement you're making, I just wonder if you could comment on this. Maybe there is no comment, and you say, well, they just prepare the state.
Yeah, I think right. The statement is that if you view it as a quasi 1D, it's only in the direction that it has non-trivial momentum that it's guaranteed to be long-range entangled. Right. So there's no contradiction, right? It could be that if you wrap it up as a in the if the long direction is x, it's long-range entangled, but if the long direction is y, it's actually not. I mean, if it's anisotropic enough, I don't see why that's forbidden. So there's no. Yeah.
But in either case, your theorem would apply, meaning you would say, well, the fact that it has a finite momentum, let's say in x direction, means that state cannot be related trivially to the product state. It must be either have a finite degeneracy or be a gapless state.
Yeah.
Okay. Thanks.
Okay. So I'm still a little worried about the fact that I consider a finite system. I mean, is there any version of a state that you can make for an infinite system?
Sorry, Dominic, can say that again, especially the last part?
Is there any version of this result that you can state in an infinite system?
Yeah, you have to, unless you know how the momentum behaves as you increase L. In fact, that was the original motivation. This whole work was motivated out of some studies on semi-metals and so on. So there, if you assume that, for example, the momentum is some reasonably smooth function as L goes to infinity, then you can make some statements. But that assumption is not always obviously correct. It may turn out to be correct in many cases, but we have no real justification. Yeah, so it's yeah, I can only make it precise, assuming finite but large system size, large compared to, let's say, correlation length or circuit depth.
Yeah, like for the U1 LSM, there's a local quantity which you can define, which is the fill-in, and then the result theorem just states that that's what happens if that's not an integer, but there's no analog of that here.
That's the thing. The thing with U1 is that it's relatively easy for that density, that Q over L, to be well behaved in the L goes to infinity limit. Right. It's essentially just For example, assuming your compressibility doesn't diverge or something like that. But for momentum, it's hard to have such a precise statement about well-behavedness of the momentum in the thermodynamic limit. I think it's quite sensitive to the detailed energetics. Yeah, so it's a bit different on that aspect.
I have another question. So I think here so far you try to show short-range entangled state carries zero momentum. Like, is there some converse statement to say, like, in which case you can say long-range entangled state can carry zero or non-zero momentum? That have a statement based on similar arguments.
I'll have some arguments. I'll have something like that soon. But in general, if it's a long-range entangled, in the most general case, you can have anything. But I'll have some statements like that later.
Just like in which case will be, maybe there are some criteria to get
for example, I can tell you that if you have a topological order in 2 dimensions, for example,
yes.
If it has let's say a q-fold degeneracy on a torus, for example, then we know that the momentum has to be quantized in 2 pi over q in any direction. So you can make statements like that. Yeah.
That's similar to Professor Oshikawa's type of statement. Or?
It's actually very similar to LSM type of thing, except you don't need other on-site symmetry, on-site global symmetries. Just translation alone is enough to tell you that. But otherwise, it's very simple. Yeah.
That's, and then presumably for that, the translation has to be fractionalized on the topological order. Is that right? To get the non-trivial answer.
Basically, yes. Yeah, I'll talk about some examples of that. So I may not have time, but yeah, we'll see.
Excuse me?
Yes.
I'm wondering, what if we consider, let's say, a one-dimensional system that we breaks, let's say that we break the translation invariance. Let's say we consider open boundary condition. Could we make any statement about the ground state of such system, like whether it's short range, entangled, or whatever? Because then we don't have a notion of momentum anymore, right?
Yeah, that's the problem. In that case, I don't know if I can make any statement of similar sort. I just don't.
Okay, thanks.
Can I ask? Sorry.
Go on. Go ahead.
Oh, can I ask one more question? So, suppose I have 2 states with opposite momentum.
Yeah.
And I take the tensor product of 2 states. So now the tensor product state has 0 momentum, right?
Yeah.
But it's still long-range entangled.
Right. My statement is that short-range entangled states cannot have non-trivial momentum. I'm not saying any state with trivial momentum is short-range entangled. I'm not saying that. Of course, there are lots of long-range entangled states with trivial momentum. Take a Fermi surface with inversion symmetry, right? That has 0 momentum, but it's metallic.
Okay, thanks.
All right, so Lieb-Schultz-Mattis, again, something I'm sure a lot of you know very well, but let me quickly go over it anyway. And for my purpose, just for simplicity, let me think about the lattice bosons with translation symmetry and U1, on-site U1 charge conservation symmetry in 1 dimension, right? Just for simplicity. The statement that I can make, I mean, it's not quite the original LSM theorem, but it's the version that's closely resembles the kind of thing I talk about here. Is that if I have a state which is an eigenstate of both, let's say, translation and the U1 symmetry, if I have a state such that the total charge since the state is an eigenstate of the total charge, the charge is just a number here. The total charge divided by system size L, meaning the charge density, is not an integer. Then the state is long-range entangled, in the sense that it cannot be created from the product state using a quantum circuit with depth much smaller than the system size. Okay. I mean, it's morally equivalent to most of the to other versions of the LSM theorem, maybe up to some tiny subtleties, but I'll use this version. Okay. So as I said, you don't have to take this lattice boson in 1D. It works for things like fermions. It generalizes to higher dimensions, and it can also work for many other symmetries. It doesn't have to be 1D. Sorry, it doesn't have to be U1. Can be others, or can even talk about, instead of translation, you can talk about things like lattice rotation and so on. But just for my purpose, let me stick with the simplest case here. Okay. And if you think about it, this is really the glorified version of the statement you learned in solid state 101, right? If you have a fractional charge density, the state cannot be a trivial insulator. With fermions, you have partially filled bands, so you get a metal. Or if you have BCS instability, you get superconductor. But in any case, you don't get a trivial insulator. So this is the glorified version of that. Even with arbitrarily strong interaction, as long as it's local, this statement is true. And this type of statements are extremely powerful for several purposes. For example, it constrains possible low energy dynamics. Right? For example, you have some horribly strongly interacting lattice model that you don't know how to solve controllably, but if it satisfies some UV conditions like this, then you know that the IR dynamics, the low energy dynamics, cannot be too trivial. It's also useful practically for identifying possible exotic states in real systems, such as quantum spin liquids. So it's something that we like a lot. So of course, this is a classic theorem. The original version was proposed in the 60s, I think. So there are many different versions, well, at least several slightly different versions of proof out there in the literature. So here, let me offer you a pretty simple proof, just from the theorem that I just told you, that any momentum, non-trivial momentum eigenstate must be long-range entangled. So the nice thing is we can also generalize it to other type of symmetries that have not been considered before, right? So let's say consider a state that's an simultaneous eigenstate of the total charge density, total charge and momentum, right? So if let's call this state psi. So if psi has non-trivial momentum, then we're done, right? It's long-range entangled. So if momentum is 0 for psi, then we can consider another state. So let's call it psi prime, which is connected to the psi through a simple local unitary here. And for those of you familiar with the business, this is nothing but the large gauge transform for the U1 symmetry, right? So concretely, U is the product of this operator. So this Q hat is the charge operator defined on each side. It will defined on each unit in each unit set, right? So so you see that because there's an X here, X is the lattice side index. It goes from 1, 2, 3 all the way to L, right? So some simple algebra will tell you that this U changes momentum, because U doesn't commute with translation, or because of the explicit dependence on X here, it doesn't commute with translation. And if you go through some simple operator commutation algebra, you'll see that this psi prime will have a non-trivial lattice momentum. Let's call it P prime. That's equal to 2 pi times the charge density. Okay, so this is a well-known trick in LSM theorem. And by our previous statement, then it means that this psi prime must be long-range entangled because it has a non-trivial momentum. And remember, the original psi only differ from the psi prime by a depth 1 circuit. This U here is a depth 1 circuit because it's just a product of unitaries of single qubit unitaries. So that's a layer 1 circuit. So a depth 1 circuit is just a special case of finite depth circuit. And if psi prime is long-range entangled, psi, which is obtained from psi prime by a finite depth circuit, cannot be short-range entangled, but by definition. So psi is also long-range entangled. That's it, right? So that's a proof for the LSM, which already has many proofs. So it adds a little bit of feature to the original LSM. I would say it's a little bit stronger than the original LSM theorem because you may notice here that I'm not even referring to any Hamiltonian here. Right? It's purely a statement about the state. For example, I don't need to worry about, if psi is the ground state, I don't need to worry about whether psi prime has a vanishing energy cost or not. Just the mere existence of it is enough to give me the theorem. And in particular, there is no need to assume that psi is the ground state of a translationally symmetric U1 conserving local Hamiltonian, right? Just psi, the only thing I require is that psi is an eigenstate of the symmetries. So it's just slightly stronger than the original. Yes.
Should I be worried that in this product is over the entire lattice sum? Right.
No,
so
but the thing is, it's a 1 layer. That's the important thing. Depth is 1, right? It involves all qubits. That's fine, right? Remember this picture, right? Each layer can involve all the products, all the qubits. That's fine, right? The important thing is how many layers you have. Order L or order 1.
Right, but didn't you always assume that, there was some statement you made earlier about the finite support, right? And I always took it to be that a finite depth also implies a finite support.
No. The finite support thing is I cut out the light cone circuit, right? This guy. The finite support means that if I only apply this gate and set all the other the gates outside of this region to 1, right? That's a finite support. Unitary.
Right, but now you take a product. Right, but now you take a product of such blue circuits, right, next to each other, right, and you keep iterating it over the entire system. Are you not worried that you're effectively getting, you're getting an infinite depth circuit in a sense that it spans the entire system?
No, the thing is, all this, the important thing is all this commute with each other, right? Q at site I, sorry, I should have a subscription QX here. Q at site X has nothing to do with Q at site X prime. So they commute.
Gotcha.
As long as they commute, this is just 1 single layer.
Yeah.
If things involve non-commuting stuff, you have to organize them into commuting layers, and then you have to worry about exactly what's your depth and so on. Here it's just depth 1.
Gotcha. Okay, thanks.
But this circuit, it's not even 2 qubit gates, right? These are 1 qubit.
Yeah, it's even simpler. Yeah, exactly. Okay, so beside the proof of, beside just another proof of the well-known, well-established LSM, one lesson we learned is that there's an equivalent formulation of the theorem I just told you, which is if I have a state psi, which is related to another psi prime with by a finite depth U, where psi prime has a non-trivial momentum, then psi must be long-range entangled, right? So psi itself may not have trivial momentum. It may not even be the eigenstate of translation. Doesn't matter, as long as it's related to a non-zero momentum eigenstate by a finite depth circuit, then that's already enough to tell us that psi is long-range entangled. Of course, this is, if you think about it, this is obviously equivalent to my previous statement, because whether it's long-range entangled or not does not change under a finite depth circuit. Right. The thing is, this way of formulation allows us to more easily make non-trivial statements about various states. Right. It doesn't. So essentially, the power of our theorem is not restricted just to momentum to states with non-trivial momentum. Even a state has trivial momentum, there are ways to apply our result and get funny and get interesting statements. Okay. In particular, I'm going to tell you a version of LSM that's kind of new. At least as far as I can tell, it has not been talked about before. Essentially, a discrete version. So the previous version I told you involves a U1 charge conservation symmetry. You can naturally ask, is there some statement like that if I restrict U1 to some discrete subgroup, let's say Zn? It turns out you can. So let me just tell you a Z2 version. It generalizes quite straightforwardly to any Zn. Sorry.
So let me just make sure. I think maybe I was, when I say maybe I will say you wrong, but let's just, I think earlier you say the intuition you are starting to do a proof is that the tensor product state, cannot under some local unitary transformation to any state carry non-zero momentum, right?
Yeah.
And then earlier slide, I just want to make sure. So if you start from maybe long range instead of tensor product or short range entangled state, can you change your long range entangled state from carry non-zero momentum to zero momentum?
Yeah.
And vice versa, you can under local unitary.
You can. Yeah. Okay. Yeah. So that's an alternative state. It's an equivalent way to state to make our statement. That is, if you want a low finite depth local unitary to boost your momentum, it only works on long range entangled state. It cannot work on short range entangled state.
Can you just say maybe these are obvious, but just some intuition? What do you think?
If you have a finite depth circuit, you want it to boost your momentum. If it works on short range entangled state, then it contradicts our statement, right? Because when you apply that finite depth short range entangled, you get another short range entangled state which should have zero momentum.
But for the long range entangle, how do you change your momentum from zero and vice versa?
For long range entangle, there's just our result doesn't make any restriction, and in fact there is no real restriction. For example, we know here that this large gauge transform does boost your momentum. Right. Actually, the simplest example is just think about a Fermi surface, a partially filled band, for example, a Fermi surface. If you make a large gauge transform, you're displacing the entire Fermi surface. The total lattice momentum is just the sum of each individual block state. So you just think about that picture, your total momentum will change under this large gauge transform.
Yes, but that is part of a local unitary transformation.
I mean, yeah, this large gauge transform. It's a depth 1 circuit. It's the simplest kind of finite depth local unitary.
Thanks. Thank you.
Yeah. All right. So the Z2 version. Essentially, so here's the statement. Let's think about it. Let's say Ising spin chain. It doesn't really have to be literally Ising chain, but it's a system, a lattice system with an on-site Z2 symmetry. So so the Z2 symmetry is generated, let's say, by the product of all the Pauli X matrices on each site. Let's say I is the site index. So the non-trivial statement here is that if you have a system with length that's even, that's 2 times an integer. Okay, and if this this state, and if you have a many-body state psi, that's an eigenstate of the translation symmetry, and it's also an eigenstate of this Z2 Ising symmetry, but with a non-trivial total Z2 charge. So acting on this psi with x gives you a minus sign. Then psi has to be long-range entangled. in the sense that it cannot be created from the product state with a circuit with a depth much shorter than the system size. Okay.
But I think it could be long-range entangled in kind of a trivial way, right? Because you could just create a single quasi-particle with a C2 charge and like take this lock state that we were discussing before, which is kind of like not really like that. I mean, technically it's long-range entangled, but it's not like some topological order or something.
Yeah, it's that state itself doesn't look super exotic, but for example, if you try to realize that state as the ground state of a local Hamiltonian, it's actually not entirely trivial how you do that. But I agree that that these things can be these constraints can be satisfied with some fairly simple states. Yeah, that I definitely agree. Yeah, so the proof goes as very similar to the previous one for the U1. The idea is, let's say, suppose psi has zero momentum. I mean, otherwise there's nothing to prove. It's already long-range entangled. So if psi has zero momentum, let's try to find a simple unitary operator, a finite-depth circuit that boosts the momentum to something else. So here there's a very natural thing to do. You just apply the charge operator, but not for the whole system, but on all the even sides. If your system size is even, this is a reasonable thing to do, at least well defined. And some very simple analysis tells you that this boosts the momentum by pi. Essentially, you can do it in real time, really, because if you translate this state, right, this xi on all even side becomes xi on odd sides. So it differs from the original state by the product of x on all sides, which by assumption is a -1 on this state, right? So so that tells you that if the original state has momentum 0, your new state, this psi prime, must have momentum pi. So psi prime must be long-range entangled, and therefore psi also must be long-range entangled. Okay. And we're done. And of course, you can easily generalize this to any Zn symmetry. And in fact, the U1 version, and that's just a side remark, follows actually also follows from this type of statements. If I restrict the U1 to the ZL subgroup, L being the system size. And in fact, if I restrict to the U1 to the ZL and I construct a similar operator like this one, it's exactly the large U1 gauge transform I displayed in the previous slide. Okay. All right, so I am pretty much out of time, but let me quickly tell you a story about topological orders in higher dimensions. So I've mostly been just talking about 1D stuff so far. I mean, the statement is intrinsically 1D. Even if you go to higher dimension, the way to look at it is to roll it up and view it as a quasi-1D state. But still, if I think about it, 2D topological order, let's say, for example, you think about the ground state or one of the ground states for a gapped topological order. Let's call it psi. And suppose it has non-trivial momentum, px, right? So we know the topologically ordered state is long-range order in 2D, so there's no problem for it to have non-trivial momentum in 2D. So when viewed as a 2D state, that's just totally fine. But things becomes a little bit funnier if you view this state as a 1D state, right? You roll it up, you view your y direction as just a large unit cell and just view it as a 1D system in x direction. Well, the statement is that since px is non-trivial, it still be non-trivial in x direction. And it's gapped. Well, it's a gapped and supposedly long-range entangled state. So it's either spontaneous symmetry breaking or have intrinsic topological order. But there is no intrinsic topological order in 1D. So the only option left is that this state, when viewed as a 1D system, must spontaneously break some symmetry. The only relevant symmetry here is the translation symmetry. So the statement is that this is actually, when viewed as a 1D, this is actually a cast state that breaks translation. It's a CDW, so charge density wave. Okay. And that's perfectly compatible with the fact that when viewed as a 2D state, it looks symmetric. Because the order parameter that gives you the symmetry translation symmetry breaking order in the 1D limit is actually could actually be some loop operators wrapping around in the y direction. So when you view it as a 2D system, it's not a local operator. It's only when you view it as a 1D system with the y direction compactified that the order parameter looks local. Right? So this is sometimes called the weak symmetry breaking. So it's a topological order that spontaneously breaks the symmetry, but it's only detectable with large loop operators. There's no local order parameter.
Excuse me. By the way, this compactify 2D to 1D in a spatial, this argument, maybe also just the previous slide, you try to say that this leads to weak symmetry breaking because there's no 1D topological order.
Yes.
But if this compactify radius is small, there could be additional states, like a Cardoza Klein.
Yeah. So I'm not trying to shrink this circle too small. I'm just saying I'm viewing the state as 1D. I can always do that. I just get a gigantic unit cell. That's it. But there's nothing wrong with gigantic unit cell.
Okay.
Yeah. Because if you actually gradually reduce this, the circle, dynamically various things could happen. The gap could close, so on and so forth. We don't know, right? So let's fix the system size. Yeah. We know it's gapped, and just view it as 1D.
And also, you also have a lattice cutoff.
Oh yeah, of course.
Yeah. Thanks.
All right, and in fact, again, this kind of statement is not only true if the psi has, sorry, let me say it again. For a topological order, we know that there are multiple degenerate ground states. So if, let's say, one of them, let me call it psi, has non-trivial momentum, then my statement is that it's a weak CDW. The thing is, for other degenerate ground states, even if they have zero momentum, they are still related to this non-trivial momentum state, this psi, through some unitary. It's some well-known unitary, some loop operator wrapping around in the y direction. For example, you can create a pair of anion and anti-anion and take the anion around the loop and re-annihilate with the anti-anion. That process will bring you from one ground state to the other. So such operators are non-local in the y direction, but they are local but they could be perfectly local in the x direction. So again, when viewed as a 1D system, they are related to this psi state through a local unitary, through a finite depth local unitary. Which means that as long as one of the degenerate ground states for this topological order, let's call it psi, has non-trivial momentum, then all the ground states in the ground state manifold must also be weakly breaking the translation symmetry. Right. And finally, let me just say that this is actually nothing new. Well, the phenomenon is nothing new. It's actually a well-known thing in fractional quantum Hall physics. The statement is that if you take the Laughlin state, let's say for nu 1/2, the simplest one for boson, and if you put it on the cylinder, but you take let's say you take the Landau gauge on the y direction, and so that the Landau orbits becomes just essentially a 1D lattice. Then the Laughlin state is adiabatically connected to a CDW state, also known as the Tao-Thouless state. It's basically this guy 0, 1, 0, 1 plus minus 1, 0, 1, 0. Right? That's the Laughlin state. And so the lesson is that the Tao-Thouless physics is it's actually just a special case of a much more general pattern. Right? So at any time you have non-trivial momentum states from a topological order, you expect something like that. And I think my time is really up. So let me wrap up. Again, the key message is that non-trivial momentum requires long-range entanglement. And there are some applications. There are two that I talked about, LSM theorems and weak CDW from topological orders. There are plenty of things that one can imagine doing in the future. For example, can we have a more rigorous proof, even taking care of the exponential tails? Or can we have more applications of this sort? Can we have more such relations, for example, for other symmetries or general unitaries, or even general operators, and so on. So let me end here, and thank you for your attention.
Thank you, Chong, for the nice talk. More question from the audience. I think we already have many questions. Comments?
So do you have a general statement about anomaly matching? I think you alluded to it a little bit.
Yeah, I don't. I roughly know how it works in 1+1. I had a hard time doing it in higher dimension. So at this point, I don't know how exactly it corresponds to Hooft anomaly. I have some vague idea, but things haven't worked out fully yet. That in 1+1D it looks just like a Chen-Simons term, but it's kind of important that you need to take the translation gauge field not as Z but as ZL. You can embed it into U1, but importantly, it's not Z. Z doesn't work.
Well, yeah, I mean that's true for the conventional LSM as well. Like in some sense, it's important that ultimately you get a compact symmetry group.
Yeah. For the usual U1 LSM, even with Z, one can fudge a little bit, but for this one, I don't even know how to fudge. Yeah.
I mean, what I want to say is this: I tell you that there's some emergent symmetry group, and let's say it's a compact group, and I tell you how translation maps into that symmetry group, and I tell you what the anomaly is, and you tell me what the momentum is. Yeah, so you're saying you can do that in 1D, but maybe not in higher dimensions?
Yeah, I don't know how to do it in general dimension. In 1D, I may be able to do it. Actually, there it's also a little bit tricky because it has to do with the issue about thermodynamic limit we mentioned earlier. The thing is, when you give me the IR theory, it's usually already contains only just thermodynamic information, not on some specific size L. So how much you can infer from there is sometimes you can, but I don't know how universally applicable things are. So things are subtle. That's what I'm trying to say.
Chong, could I ask a very quick question about the Tao-Thouless state?
Yeah.
So do I understand correctly that it's essentially a cat state, correct? As written on the previous slide?
Yeah, it is.
And does it have a definite value of momentum? No, it doesn't.
Well,
right?
with the plus sign, it's 0. With the minus sign, it's pi.
That's right. Okay. And then this is an example from your Z2 example, right? There are two states that are connected by pi, and therefore both must be long-range entangled.
Yeah.
Okay. Right. And do you know if that maps also on Majumdar-Ghosh state? Because you could similarly think, I mean, if you by 0 and 1, you think of as it's an odd or even sign that participates in a given singlet, right? You could also think of the two coverings of a finite, let's say finite or infinite chain on the ring.
Actually, I don't know much about that example. Yeah, I haven't thought about those type of states, but
yeah, that's good. Thanks.
Yeah.
Okay, so I think we should thank Chong, and people can still stay for discussion. Thank you very much for the great talk. Thank you.